This is my first progress presentation about my research project for this semester called Waveguiding on Surface Gravity Waves. My name is Edgardo Rosas and my advisor is Professor Claudio Falcon. So here's the outline for this presentation. First, I want to talk about the theoretical problem, but in a different way from last presentation in order to be more clear with that. After that, I will talk about the progress and the things that I have done last week, then the objectives that I have now, and some things that I have in mind now, and the scale to aim that. So here's the governing equation for my problem. It looks very complicated, but now I will try to explain it. So we have to keep in mind that here we have two variables that we are looking for. The first one is this phi that represents the potential velocity for the water, and eta that is the water surface, the displacement from the equilibrium for the surface of the water. So we have these two variables that we are looking for, and all the other are parameters. For example, this is the depth of the water over the waveguide. This is the depth of the water out of the waveguide. This A is the width of the waveguide, and G are the acceleration of gravity. So we have this principal PDA equation for potential velocity phi that is valid for all z between the bottom and the water surface. Then we have a kinematic boundary condition that is valid at the surface of the water. Then we have a dynamical boundary condition at the surface of the water. And this is a kinematic boundary condition at the bottom over the waveguide in this case, and the same but out of the waveguide in this case. And finally, we have this kinematic boundary condition in the change of depth. So this problem is very difficult to solve, mainly due to two reasons. The first one is that we have here and here nonlinear terms. For that, in general, nonlinear terms are difficult in differential equations. And the other things that make it hard to solve is the things that happen on the depth of the water. So for these two reasons, this is very complicated to solve. So the first approach that we can do is ignore the nonlinearity and ignore the things that happen on water depth. In this case, we have this linear and shallow wave equation that is the simplest model that we can consider when we are looking for traveling waves. So these have this dispersion relation, and if we are interested in the propagation modes, we have to solve this transcendental equation. So after that, we can consider this problem that on which we are ignoring the nonlinear terms, but consider the things that happen on water depth. This is the problem that I have been studied in the summer internship at the university. So when I solved this problem, before we can summarize this kinematic boundary condition and this dynamical boundary condition on this term. So we have this all the boundary condition for the problem, and when we solve this problem, we can obtain this, that is the dispersion relation for the waves that are traveling on this model. And if we are interested in the beta, that is the propagation modes over the waveguide, we have to solve this transcendental equation that, as you can see, this is quite more complicated than the equation that we saw before. So now I am interested in what happens when we consider these nonlinear terms. But as I said before, this is so complicated. So for that reason, we will do some approximation. The first is that we will not be interesting in the things that happens on water depth, like in the first model that I showed, like in here. But the difference is that in the problem that I'm studying now, we will be interested in the non-linearity that appear here. So this is the thing that I have done last week. Try to understand the derivation of this equation, and for that reason, I guess this type of solutions, that is a perturbative solution, and then a lot of algebra and a lot of work and some approximation, we obtain this equation that is nonlinear. We have this term that is in equilibrium with this dispersive term. So this equation have this type of solution. Due to this formula, we have this is the shape of this type of solution, and usually it is called a solitary wave or a soliton. So one thing that is very interesting for this type of wave is that velocity depends on the amplitude of the wave, that in this case is constant. So the next step on this research project is try some Kalomstempet-Viashvili solution for the problem, because this problem is one-dimensional, and we have in the real problem one more dimension. So we have to consider another dimension, spatial dimension. And the first thing that I want to do next week is try this type of solution. This for the things that happen over the waveguide, and these two things that happen out the waveguide. So maybe it will not work, but it would be interesting to understand what's going on with these solutions. So the schedule is there. We are on week 8, and we are doing this task. So for now, I am good with time. Well, these are the reference, and thank you very much.